Great. So welcome back. So today I want to talk about the following ingredient in the disproof of the telescope conjecture. So I want to recall from last time one of the key steps. Uh, so one of the key steps in uh, one of the key steps in disproving the telescope conjecture was the following square. So there's this there's this object which is TC of some ring spectrum. Some ring spectrum where you it was like BPN, and you took the fixed points of it by some automorphism, some Adams operation, and you can take that and you can tensor it with a type n+1 telescope. And what we wanted to show was that TC did not commute with the limit of taking this fixed points. So we wanted to show that this map going to TC of Rn with the fixed points on the outside is not an equivalence. That's what we wanted to show. And one of the key steps in showing this, so enough to show that, for example, on pi star, it's not an isomorphism. But one of the key steps was to sort of replace this action, which is a non-trivial action, by Adams operations with a trivial action. So the claim was that if you choose your Adams operation correctly, then you're allowed to replace this map that you wanted to show as not an equivalence. This map was essentially the Kn+1 localization map, or the cyclotomic completion map. So you want to show that this map's not an equivalence. And the claim is that it's enough at the level of pi star to check it for the trivial action if you choose your Adams operation correctly. So BZ just means the fixed points by the trivial action. And so what I want to explain today is, so today we'll see why it's easier to show this map isn't an isomorphism. So yeah, so why did this commutative square help us? Sorry. And the claim is that this map is a lot easier to show it's not an isomorphism. Okay. And so I didn't even define TC in the last lecture, so maybe I will begin by sort of recalling some of the basics about TC and some just a quick recap of how this works. So let's do some reminders. It's TC. So TC was some invariant of a ring spectrum, and I will explain roughly how it's constructed. So just some notation. We're going to use T to denote a circle as a group. And so there's sort of various subgroups of the circle, for example, the cyclic groups of order p to the I. And really, I'm going to work, everything I'm going to talk about today is going to be p completed, okay? So so you can look at a circle, a spectrum with a circle action, which I'm going to denote the category of circle equivariant spectra, like this. And given a spectrum with a circle action, or really just a Cp to the I action, you can form the orbits and you can form the fixed points. And there's a map between them, which is this norm map. And then you can take the cofiber, which is the Tate construction of, and this map is called the canonical map. And these are lax symmetric nodal functors of X. And so if X was actually a circle equivariant spectrum, then these have residual, these actually, all of these maps live in, they're equivariant spectra with respect to the quotient group. which is also a circle. It's the circle modulo the cyclic group of order p to the I, which can be identified with also just the circle. Okay, so the definition of a key definition is the category of cyclotomic spectra. So this definition is due to Nicolaus and Schulze. And the definition is that a cyclotomic spectrum, it's a circle equivariant spectrum. And really here, everything is P complete. So maybe I'll emphasize that here. And a circle equivariant Frobenius map from X to its Tate construction, which is viewed as a circle equivariant spectrum and as above. So this is a map in circle equivariant spectrum. Okay. So this is due to Nicolaus and Schulze. And the key point is that TC is constructed in some sense using this category in the following way. So if you start with an algebra in spectra, so just an associative algebra, there's this functor called THH, which lands inside cyclotomic spectra. And so any cyclotomic spectrum has an underlying spectrum, namely just the underlying object X. So there's sort of a forgetful functor to spectra. And this composite I can describe. So it sends an object R to R tensored over R tensor R up of R. Okay, and so here you're viewing R as an R bimodule in two different ways. And so that's THH, and now so it gives you, so the claim is that this formula, which is THH of R, actually gives you a cyclotomic spectrum, not just a spectrum. So there's a circle action on it, and there's this Frobenius. And I'm gonna make a bit explicit what this is in the case that R is a commutative algebra. So if R is actually a commutative algebra, so an E-infinity algebra in spectra, then it's actually a lot simpler to describe THH. So namely, THH of R in this case is it's the co-limit of the constant diagram over the circle of R in E-infinity rings. So maybe I'll just say in commutative algebras in spectra. So, okay, yeah, so maybe I will just point out that these are symmetric monoidal functors. Symmetric monoidal. So in other words, if you have an E-infinity algebra, you actually get a commutative algebra in cyclotomic spectra when you take THH, and that the underlying spectrum, the underlying commutative algebra in spectra is just the constant co-limit over R in commutative algebras. And now it's very apparent what the circle action is. The circle action is just coming from the fact that the circle acts on itself by rotation. And so what you can also observe is that the fact that you're just taking the co-limit over the constant diagram of the circle, that's sort of saying that there's a map from R to THH of R, which is just choosing some point on the circle. And this map is sort of the universal E-infinity map into a circle equivariant E-infinity ring. So it gives a universal property of THH as a circle equivariant E-infinity ring. And you can use that to actually define the cyclotomic Frobenius in this case. Namely, you can do the following. So there's this natural transformation in spectra. It's a natural transformation from the identity functor. So for any spectrum X, you get a natural map from X to the tensor P, and then you take the Tate construction with respect to the cyclic group that permutes the different factors. So this map is called the Tate diagonal. This is the Tate diagonal. So this is just some natural map that you have for every spectrum, and it's a lax symmetric monoidal functor. It's a lax symmetric monoidal map. And what you can do now is if you have some E infinity ring R, you can apply the Tate diagonal to get a map to R tensor, an E infinity map to R tensor P TCP. But now R tensor P you can view as the co-limit over the cyclic group of order P in the infinity rings. That's what the R tensor P is. And so from the inclusion of the cyclic group of order P into the circle, you get a map just by uh, taking the co-limit over these constant diagrams and then taking TCP. You get a map from this into THH of R TCP. So now this composite map, so this has a residual circle action. And so this uniquely factors using the universal property of THH as a circle equivariant infinity map like this. And that's the Frobenius map. Okay. So the Frobenius map is characterized as the unique circle equivariant infinity map that makes this diagram commute. Okay, so I told you that the category of cyclotomic spectra is a symmetric quinoidal category. So let me just briefly describe the unit inside of it. So the unit inside the symmetric quinoidal category of cyclotomic spectra is the following thing. You take the P-complete sphere and you map via the unit map, which is the Frobenius, into the Tate construction of the trivial action on it. So the B-complete sphere has a trivial circle action. You just take the Tate construction with respect to that, the circle on it, and then it's Frobenius map. And there's this fact, which is the Siegel conjecture, which is that this is an isomorphism. So yeah, so this is a non-trivial fact that in this case, the Frobenius map happens to be an isomorphism. And in fact, this cyclotomic spectrum is also THH of something, namely this is just THH of the sphere spectrum, or P completed. Okay, so now what is TC? And I can tell you what TC is. So TC is just defined. So I'll define it for a cyclotomic spectrum first. So TC of a cyclotomic spectrum is defined as maps and cyclotomic spectra from the unit, which is this object, into X, which you can equivalently write as the equalizer of you have X, you have the fixed points of X by the circle, and then you can map, there are two different maps, a canonical map and a Frobenius map, to you take the Tate construction by the cyclic group of order P, and then you take the fixed points by the residual circle action. And one of these maps is just coming from it's coming from exactly this canonical map up here from the homotopy fixed points of CP to the Tate construction on CP. And then the other one's coming from taking the fixed points of the Frobenius map. Okay, so that's TC. And let's recall what we're interested in. Oh, so sorry. So maybe I should say TC of some ring is just TC of THH of that ring. So if I input a ring instead of a cyclotomic spectrum, then I just mean TC of the THH of that ring. Okay, so what we want to understand, what we're interested in understanding. So we wanted to understand what is this map from THH of some ring when you take the fixed points by the trivial action, trivial Z action. What is this comparison map, this sort of this co-assembly map that takes this to THH of R, and then you take the fixed points on the outside? Well, we were interested in understanding this map at the level of TC. That's what we were interested in. And the first thing to observe when trying to understand this question is that it actually reduces to try to think about, it reduces to sort of understanding a universal example. And that's because THH is the symmetric monoidal functor. And so you can, in fact, write this as just THH of R tensored with, or really this whole map, I guess, is as THH of R tensored with the following map. So you can take THH of the sphere to BZ and then map to THH of sphere to the BZ. And so, yeah, so really we just need to study this universal example and then we can just tensor it with the ring that we're interested in at the end. Okay, and so that's the approach that we'll take. Okay, so let's first just try to understand what is this maybe as an E infinity ring? What is this THH of S to the BZ? So let's remember the definition. So the definition was that you take S to the BZ, you tensor it over S to the BZ, tensor S to the BZ with S to the BZ. Okay, that's what we're trying to figure out. And well, you can just put these. There's a Kunitz formula, so you can put these together to see that this is just S to the BZ tensored over S to the BZ times BZ, S to the BZ. Okay, so here's the first observation. So these maps that we're tensoring along, they're coming from the map from BZ times BZ. Like this BZ is the circle. So it's coming from the multiplication map on the circle, or the addition map, whichever one you want to call it. I'll just call it mu. And the point is that this map is actually isomorphic to just a map that's projection along one of the factors. Namely, there's sort of a shearing map that you can write down, which is just given by the matrix like 1, -1, 0, 1. And that's an isomorphism to the projection on one of the factors. And so what that's telling you is that this tensor product that we're trying to compute, you can instead of using this multiplication map, you could have used the projection map. And then what you would have gotten is something that breaks up as a tensor product of two things. Namely, you get S to the BZ tensored over S to the BZ, with S to the BZ, tensored with the projection, which is S tensored over S to the BZ, with S. Okay. And maybe just to simplify that, that's S to the BZ tensored with this thing. Okay. So in other words, there's a copy of the cochains of this is the cochains of the circle. And then there's this other term that we still have to identify. Okay. So let me try to explain what this is. So to identify this term, I want to make a definition that will just be convenient. So if A is a perfect ring, a perfect FP algebra, so in other words, it's an FP algebra for which the Frobenius map is an isomorphism. Then there's an E infinity algebra called the spherical width vectors of A, and it's a commutative algebra in P complete spectra, and it's connective, and it's uniquely characterized by the fact that it comes with an isomorphism from the spherical width vectors of A tensored with FP to A. Okay. So this is some construction. So for example, if I take A to just be FP itself, the spherical width vectors is just going to be the sphere, the P complete sphere. But if I take it to be like, let's say, a product of FP, a finite product of FPs, then it will just be a finite product of spheres. And so this is some functorial construction. So the claim is that you can use this to describe this tensor product. Namely, the claim is that if you take sphere tensored over sphere to the BZ with sphere, it's the following thing. It's the spherical width vectors of the continuous functions on ZP. And so what is this continuous functions on ZP? It's so ZP has a topology, and when I say continuous functions, I mean continuous functions from ZP with its p-adic topology to FP with its discrete topology. So these continuous functions under pointwise multiplication and addition form a perfect FP algebra. Okay. And I mean, this might look like a very fancy thing, but it's really very simple because it's really just the following thing. So you can take the co-limit in NP-complete infinity rings over n of just functions from z mod p to the n to the sphere spectrum. So this is just a finite product of copies of copies of the sphere. And you're just taking the co-limit as n goes to infinity. And that's all this is. It's just it's a co-limit of products of copies of the sphere. Okay, so that's the claim that these are the same. I'll sort of explain why. So the first thing to observe is that this tensor product is connective. It's a connective E infinity ring. And that's just because this thing it's -1 connective, and whenever you have a connective ring and you tensor it with over a -1 connective ring with the connective ring, you always get something connective. So okay, so this thing is connective, and so I told you a characterization of the spherical width vectors. It's characterized by being connective, p complete, and you can just check that its FP homology is what you think it is. So the fact that this is connective tells you that it's enough to show the result. It's enough to show the claim after you tensor with FP. Okay, so let's understand these things after tensoring with FP. So after you tensor with FP, I can replace all the spheres with FPs. So then you get FP tensored over FP to the BZ with FP. Okay, and let's think about this. So this is the cohomology of a circle. And you can write BZ in the following way. So the thing to observe is that the cohomology of the circle is in fact the filtered colimit of the cohomologies of the cyclic groups of order p to the n. Namely, so I claim that this is just the fact about group cohomology. So fp to the bz is the colimit over n of fp to the b z mod p to the n. Okay, and that's because, I mean, these cohomologies are essentially an exterior generator and a polynomial generator, and the transition maps just send the polynomial generator to 0 every time. And so the colimit just has the exterior generator, which is the cohomology of the circle. Okay, so that tells you that this you can write as the colimit over n of fp tensored over fp to the bz mod p to the n of fp. But now because this has finite homotopy groups now, finite p homotopy groups, the Eilenberg-Moore spectral sequence converges. And so what that tells you is that, so the Eilenberg-Moore spectral sequence is asking if I have a pullback of spaces, well, that converging is saying that if I have a pullback of spaces, then I get a relative tensor product at the level of cohomology. And so what that tells you is that this is just the colimit over n of the loop of the cohomology of the loop space of bz mod p to the n. but that's just fp to the z mod p to the n, which is exactly continuous functions on ZP. Okay, so this step was convergence of the Eilenberg-Morris spectral sequence. Okay, so what did we learn overall? So we learned that THH of S to the BZ is spherical width vectors of continuous functions on ZP tensored with S to the BZ. Okay. So that was a calculation, but now I want to step back for a moment and think why is this the answer? Like why would you expect this to be true? And here's sort of philosophically why you'd expect something like this to be true. So we were looking, I mean, the thing that we were looking at was it was cochains of something. And so we have this cochains functor from spaces op into commutative algebras and spectra. And yeah, so it just sends x to s to the x. And we were interested in taking THH, which is the colimit over the circle. And so you could hope that maybe this functor commutes with colimits. So if it commuted with colimits, or rather the failure, whether or not this functor commutes with colimits is determined by this comparison map. So you have a comparison map over the colimit of the circle of s adjoint x, of s to the x, to s to the limit, the constant limit over the circle of x. And this constant limit of the circle is called the free loop space of x. So the free loop space of x is just the space of maps from the circle into x, unpointed maps from the circle into x. And so some sort of proxy to what THH is, THH of some cochain algebra is it should look roughly like maybe it should look like this. That would be your first guess as to what it would look like. And why does that give a similar answer? Well, if you look at the free loop space of BZ, so those are just maps from the circle into the circle. Well, that breaks up. It has infinitely many components. One, which is each component is measuring the degree of the map of the circle mapping to itself. And then pi1 of each component is just a copy. It is another copy of Z. So this is the free loop space of BZ. And so what you get is you get a comparison map from THH of S to the BZ to sphere to the Z tensor, so functions from Z to the sphere tensored with sphere to the BZ. And so maybe your guess is actually quite similar to what the correct answer is. So the correct answer was that it looked like S to the BZ tensored with continuous functions from ZP into the sphere. But this is just all functions from Z to the sphere. And maybe one way to see that this cannot be the right answer is just that these functions, if you look at all functions, you get something that's this is uncountable mod p. Whereas you sort of, because THH is built from tensor products, which only use sort of colimits or like maybe countable colimits, this thing has to be countable mod p, so it had better be something more like continuous functions as opposed to all functions. And so really, this is just some continuous version of cochains on the free loop space of BZ. That's what you learn from thinking about this. And so what this indicates is that that all of the cyclotonic structure can somehow be understood via thinking about the free loop space on BZ. Okay, so for example, the free loop space on BZ has a circle action coming from rotating the circle that you're mapping in, and that should correspond to the circle action on this ring. Okay, and I'll get into that a bit more in a little bit, but maybe I'll start with a simpler example. So you can, for example, we're interested in understanding what is the map from THH of S to the BZ into THH of S to the BZ. And we can understand this map by thinking about the free loop space on BZ. Namely, we have this comparison map to S to this free loop space of BZ. And similarly, this also compares to just S, like the S to the BZ. And this map is an equivalence because THH of the sphere is the sphere. And so what is this map? We can figure it out by thinking about a free loop space on BZ, namely what this map is coming from the following thing. So this map was coming from, you have a point inside of uh, inside of the free loop space of BZ, and for each point of the of BZ, you get a map from the circle into BZ, which is the constant loop. Um, so and you can take that co-limit. You can take the co-limit over all of the points of BZ of these constant loops mapping in. So these are sort of the constant loops. Um, and you can see that that's sort of exactly what this comparison map corresponds to. And so this co-limit is exactly just BZ itself. And this map is exactly obtained from taking cochains of this map. But you can see that this map is exactly the inclusion of the zero component of Z times BZ. Oh, yeah. Okay. And so what you learn is that you learn that this map that we were interested in, let's call it F, you learn that F is in fact the following map. It's so remember this, we identified THH of this with the spherical width vectors of continuous functions on ZP tensored with cochains on the circle. And what this is saying is that you can identify this map that we're interested in with sort of the evaluation at zero. Um, and what does that mean? It means that it means that you apply the width vectors functor to the map from continuous functions on ZP to FP that takes a continuous function and just evaluates at zero. So if you apply that to here, then you get a map from the spherical width vectors to the sphere. Okay. Okay, so let me know if there are any questions. Um, okay, thanks. So I want to make a remark about this ring. So so let's consider what a module over this ring looks like. So I want to claim that we can think of a module over the string of continuous functions on ZP, with vectors of continuous functions on ZP, as it's sort of a continuous family of spectra, of p-complete spectra, I guess, if we're working, yeah, parameterized by ZP. Okay. And what do I mean by that precisely? So if I have X, let's say, which is a module over this ring, then I can form, if I have an element in ZP, then I can form X evaluated at I, which is just X tensored uh, over the spherical width vectors of discontinuous functions with the p-complete sphere via the map that's given by, or maybe I'll just write the p-complete sphere as the spherical width vectors of Fp via the map that's given by evaluation at I. And so for each point of ZP, you get a spectrum, which is this tensor product. And the claim is that you can think of this object as being some way of gluing together all these different xi's in some continuous way. Uh, I mean, so for example, you can just see that like if you have a map of modules over this ring, then it's going to be an isomorph. If it's going to be an isomorphism, if and only if it's an isomorphism at each of these at each point in ZP. That's some fact that's something you can see. So more generally, if you have some subset of ZP, then you can look at X tensored over with vectors of continuous functions on X, mapping to spherical with vectors of continuous functions on S, and that I'm just going to denote by X restricted to S. Okay. So it doesn't have to just be a single point, but it could be many points of ZP. So, okay. So now I want to, I think I don't have a ton of time, so uh, I'm going to tell you the results of trying to think about what the circle action on THH of S to the BZ is. But you could try to work through it yourself by just thinking about the free loop space or convincing yourself that it's true. But okay, so let's try to understand. So the point is that, yeah, so the point is that we have this comparison map to cochains on the free loop space of BZ, and this is circle equivariant. This is, and so we can kind of probe. So we want to ask how does the circle act on maps from the circle into BZ? Well, the point is that if you have on the ith component, so this recall is just Z times BZ, and this Z is recording the degree of the map. And so on the ith component, it rotates, the circle acts by rotation. It acts by rotation at speed I. So in other words, it acts via this map, modding out by the cyclic group of order I. And so, for example, well, okay. So, for example, what you learn is that the action is free is free on for I equals 1. I equals 1. And so ultimately we're interested in this object, which is sort of a p-adic object. And so p-adically, all that's really relevant is the p-adic valuation of this I. And so the fact that this action is free for I equals 1 tells you that really for anything, and if you restrict this to any point which has p-adic valuation 1, the action will be the free action on a circle. So maybe I will just state precisely what I mean. So if you take THH of the sphere to the VZ, so recall that we can restrict this to subsets of ZP because of the fact that it's a module over this ring. So what we can do is we can restrict it to ZP cross. And in particular includes the point 1. And what you'll see is that the action here is free, namely that this is isomorphic to just the spherical width vectors of the continuous functions on ZP cross. That's the ring it's a module over, tensored with a -1 suspended free action. So namely just the circle acting on itself freely. This is sort of a circle equivariant isomorphism. So this is as T equivariant spectra. Okay. And so now for what happens on the other components, well, here's an observation, which is that there's this map that we haven't really considered yet from THH to itself, which I'll call the psi p, which is it's coming from taking so THH is the colimit in the infinity rings of the circle, but you could have taken the colimit in the infinity rings of the circle but parametrized p times faster. And there's this comparison map. And what that gives you is it gives you a map from THH of S to the VZ to what I'll write as P upper star of THH of S to the VZ. And P upper star just means that I take the circle action on this and I view it as a circle action via this map. So I reparameterize the circle action. See, so you have this interesting map, and what you can see by thinking about the free loop space is exactly that this gives you an isomorphism from THH. So this map gives you an isomorphism from THH to SPZ restricted to PZP to just P star, P upper star of THH of S to the BZP. So the reason for this is because if you have, so a point in here is like having a loop. You're looking at the maps from circles to circles that have degrees that are multiples of P. But if they're degrees multiples of P, then they factor through this map. They factor through this degree P map. And that's why this is true. And so what you learn from this is that, so you learn, well, this PZP is exactly the complement of this CP cross. And so what this is telling you is that because we know what THH looks like on ZP cross, we actually know what we can sort of rescale the action and figure out what happens on P to the K ZP cross for each K inductively. And so what you learn from this is that if you restrict to P to the K ZP cross, you get something very similar, namely you get continuous functions on P to the K ZP cross. And it's not quite a free action anymore, but it's free up to the fact that you rescaled from the torus modulo CP to the K. Okay. And so that's so this sort of describes the circle action on on these components, and then the circle action on I guess there's also the 0 point, and there the circle acts by it acts trivially. Okay, so maybe let's think about what the take construction on THH is now. So what is THH of S to the BZ? Tate CP. So the take construction has the property that it's going to send any object with a free action to 0. And so what we saw was that on ZP cross, that action was free. The action of the circle was free. And so in particular, the action of the cyclic group of order P is also free. And so what that tells you is that this take construction is actually the same as what you would have gotten by restricting to PZP and then taking the take construction. So you can first restrict to PZP and then take construction, because the ZP cross part is all free action, and so it cannot contribute to the take construction. But now if you restrict to PZP, we saw over here that that's the same as P upper star of THH of S to the BZ. P. But P upper star is something that gives, like, if P upper star of any circle equivariant spectrum has a trivial CP action, because it's exactly, you're pulling back along this map. And so the cyclic group of order P is going to is in the kernel of that map. And so you're really just taking the take construction by a trivial action now on these components. And so what you learn is that this is actually just so now the point is that the Siegel conjecture, which I mentioned before, is going to tell you that because this is a trivial action, this is actually just THH of S to the BZ. So this take construction doesn't do anything. Okay. So this is the Siegel conjecture. Okay. So let's try to understand the Frobenius a little bit. And I'll just give you a rough idea of it. So the key thing to do is to consider the following diagram. So it's exactly this diagram that I drew at the beginning of the lecture, which characterizes the cyclotomic Frobenius. So we have this Tate diagonal map from the ring to the p tensor power of the ring, Tate CP. And the cyclotomic Frobenius it's the unique map that makes, it's the unique circle equivariant map that makes this diagram commute. Namely, this is coming from the inclusion of the circle, the cyclic group of order P into the circle and taking the colimit. And the cyclotomic Frobenius is the unique map that makes this diagram commute. And now what we can do is we know what this is now, right? We know that this via this map, which is this coming from the degree P map of the circle, we know that this is just isomorphic to P upper star of THH of S to the BZ P, PCP, which we saw is the same thing as just, sorry, I put a ZP here, which is just the same thing as THH of S to the BZ. So this is just what we did up here. So we had this map. This map that we saw gave this equivalence that identified what this target is. But we can see that this map is actually compatible with the multiplication map here. So there's a multiplication map from here to just S to the BZ. And that's compatible with this degree P map on the circle. And so you get a commutative square like this. And this again is just S to the BZ by the Siegel conjecture again. And so what you learn is that, and so now maybe the thing to observe is that this map over here, this composite map is actually just the identity. And so what you learn is that this map that we're interested in is the unique circle equivariant map that makes this diagram, that makes this big outer square commute. And so it really just has to be the identity again, or it has to be an isomorphism at the very least. Yeah. And so what you learn is that phi is just an isomorphism. Um, and if you think a little bit more carefully about how this isomorphism works, you can see exactly what it's doing on when you restrict to different subsets of ZP. Namely, what you can see is that phi actually gives an isomorphism from THH of S to the BZ if you restrict to P to the K ZP cross. It gives an isomorphism from that to THH of S to the BZ restricted to P to the K plus 1 CP, TCP. And so it sort of this Frobenius map decomposes. It sort of shifts the location in ZP that you're at by a factor of P. And so what you learn, so now we kind of understand everything. I'll explain in what sense. So we were interested in this fiber we were interested in understanding the failure of this map to be an equivalence, this limit comparison map, right? And so we're interested in really the fiber of this map of cyclotomic spectra. So this is what we wanted to understand, and now we understand what it is as a cyclotomic spectrum, namely. So this map was given by evaluation at 0. And so the fiber is exactly everything that's away from 0. And so the fiber is exactly the direct sum over K of THH of S to the BZ restricted to P to the K ZP cross. Because the union of these subsets is exactly everything in ZP except for 0. And we now know what each of these pieces is. So it's so this is the direct sum over K greater than or equal to 0 of the following thing. So you can take well, what I wrote it up here. It's exactly what I wrote up here. So I'll just copy that down here. So it's the -1 suspension of S to the of sort of an action that's not quite free, but it's free up to a cyclic group of order P to the K. And then you tensor with the spherical weight vectors of this continuous functions on ZP cross on P to the K ZP cross. Okay. And then we also understood the Frobenius maps, namely the Frobenius maps kind of just identify they just identify what I mean they give these kinds of equivalences. And so okay, an equivalent way of describing this is that this fiber is also just equivalent as a cyclotomic spectrum to the following thing. So it's the spherical width vectors on the continuous functions of ZP cross tensored with the -1 suspension of a certain cyclotomic spectrum that I'm going to call LP to the infinity of the sphere. And I'll describe what the cyclotomic spectrum is. It's very simple. So it's the following thing. The underlying circle equivariant spectrum is just the sum from k is greater than or equal to 0 of of these of, of the circle acting at this speed, at speed p to the I, or sorry, p to the k. So this is the underlying circle equivariant spectrum, and then the Frobenius map is exactly the map that identifies, it's the direct sum of the maps that identify this with the next one, TCP. And it's okay in the sense that in this case, TCP does commute with this infinite direct sum. Sorry, I wrote the wrong thing here. This is a CP to the K, and this is a CP to the K plus one, TCP. So that's what the Frobenius is sort of the sum, it's the sum of these, okay? So this is some cyclotomic spectrum. And you can see that this description as a cyclotomic spectrum is just, it's essentially just a bunch of copies of the cyclotomic spectrum, maybe shifted down by one. Okay. And what's so nice about the cyclotomic spectrum? Well, it's actually pretty closely related to the unit in the following way. So there's a map called F from this cyclotonic spectrum to itself. And I'll tell you what it is. All it does is it sort of, it shifts degrees by one, namely, it sends this copy, this summand of this object to the next summand. And it's the degree p map. It's sort of the degree p map on the circle. And that's compatible with the Frobenius. So we had this Frobenius map, which sort of took this to the next summand. And yeah, so this diagram commutes. Okay, that's two. Okay, so this is some endomorphism of the cyclotomic spectrum. And now you can take the cofiber of one minus this map. And what you can see is that the underlying spectrum of that is it's the colimit, it's the filtered colimit over K of the degree P maps on this circle. So it's the colimit of this under the degree P maps, but we're working p-adically. And so the filtered colimit of these degree P maps is just the sphere. Because p-adically, you're not allowed to rationalize without just becoming zero. So this is just the sphere. And so what you see is that this cofiber in cyclotomic spectra is actually just, so in fact, this is just the unit in cyclotomic spectra. Okay. And so this kind of finishes what I was, this finishes the point that I was making at the beginning. So the point is that we were trying, let's say that you want to, so what do you learn from this, right? So what you learn from this is that the unit is in the thick subcategory. So it can be built infinitely many steps of the fiber of THH of the sphere to the BZ, sorry, sphere to the BZ, mapping to THH of sphere to the BZ. And so what that tells you is that if, for example, you wanted to check that TC, maybe Tn plus 1 localized of some ring, if you want to check that this limit comparison map, so sorry, if you wanted to check that the Tn plus 1 local K theory, or TC of R to the BZ, if you want to check that that's not the same as the Tn plus 1 local TC of R to the BZ, then it's enough to show that that this is not zero. So if this is not zero, then this cannot be an isomorphism because the fiber has this in its thick subcategory. Uh, and I mean, and it's really a little bit, it's even better than that in the sense that the fact that I gave an explicit formula in cyclotomic spectra for this fiber really means that you can really just compute both of these terms. Like if you knew how to compute TC of R, you can probably also just compute TC. You can probably just compute both of these terms directly because you're just tensoring with a pretty simple cyclotomic spectrum and then taking TC. Um, okay, maybe I will stop there.